Okay, so we're going to learn about Gaussian elimination. So we'll learn how to solve a system of linear equations using an approach called Gaussian elimination. This approach uses a mathematical tool called a matrix. A matrix is any rectangular array of numbers arranged in rows and columns, written within brackets. The rows of a matrix are horizontal and the columns are vertical. So for example, we have the matrix 1, negative 3, 8, 2, 5, negative 1. Once again, our rows are 1, negative 3, 8, and the other row is 2, 5, negative 1, where we have column 1, 2, and negative 3, 5, and 8, negative 1. So each, and then we have another matrix here with 3 rows and 4 columns. Each entry in a matrix is called an element or an entry of the matrix. And a matrix with m rows and n columns has size or dimension m by n. And so in this particular example, this first one on the left here has 2 rows, so we would say it's a 2 by 3 matrix because it has 2 rows and 3 columns. The second matrix has 3 rows and 4 columns, so we would say it has dimension 3 by 4, or the size is 3 by 4. The way we use matrices in this approach here is we set up something called an augmented matrix. And so consider the following. We have a system of linear equations. So x minus y equals 4, 2x plus y equals 5. That's our system. Right? We have 2 equations and 2 unknowns. Its augmented matrix is the matrix 1, negative 1, 4, 2, 1, 5. So if you notice, the first column here has a coefficient of 1, 2. That corresponds to the first column here, which is 1, 2. And the second column in our matrix corresponds to the coefficients of negative 1 and 1. And the constant terms here, 4 and 5, correspond to the third column here, 4, 5. That's the augmented matrix. So once again, these were the coefficients of x. This one here was the coefficients of y. And these are just the constant terms. So each column corresponds to that. And the rows correspond to the equation. And so that's how the augmented matrix works. Let's look at an example. Represent each system using an augmented matrix. We have the matrix 3x plus y equals 11. The second equation is x minus 8y equals 0. So the augmented matrix would be 3, 1, 1, negative 8, and then 11, 0, the 3 columns. And then I like to put a little dotted line here, dashed line. That just indicates where the equal sign was. And so that's the augmented matrix for the first system. The second system here, we have actually 3 rows this time. We have a coefficient of 2, 9, and 1 for our x's. So the first equations, we have 2x, 9x, and x, so that corresponds to coefficients 2, 9, and 1. The second column is a y coefficients. The first equation has a y coefficient of 1. The second equation does not have a y, so we have to interpret that as being a 0 coefficient. And then we have a negative 1 in the third coefficient for y in the third equation. And then z, for the first equation, we have a negative 3 for a coefficient, 4 for the second equation, and a negative 6. And then we have a negative 3 constant term for the first equation, 2, and a negative 7. So when you're writing the augmented matrix, make sure it's in standard form. Each equation is in standard form. All right, so that's how you write the augmented matrix for these 2 systems. Okay, so to solve a system of linear equations using matrices, the idea is we transform the entries to the left of the dashed line in an augmented matrix into an equivalent matrix that has 1s down its main diagonal and 0s in all the entries directly below that diagonal. A matrix written in this form is said to be in row echelon form. So for example, if we have these two augmented matrix, the idea is you want to get ones down the main diagonal and 0 below it. Your A, B, and C are just some numbers, whatever they might be. And so the second augmented matrix here, once again, the main diagonal are these ones here. And you notice the zeros below the main diagonal. So that's called row echelon form. To transform an augmented matrix into a row echelon form augmented matrix, we could use what's called row operations, sometimes stated as elementary row operations. There are three types. Type 1, any two rows of a matrix can be interchanged, and I like to denote that as Ri gets swapped with row J. So row I gets swapped with row J. Type 2, any row of a matrix can be multiplied by a non-zero constant to get a new matrix, or excuse me, a new row. So for instance, we could take any constant C, multiply the row of an augmenting matrix to get a new row, Ri. Okay. Type 3, any row of a matrix can be changed by adding a non-zero constant multiple of another row. So I like to say, okay, we could take row I and then multiply, say, row J by a constant and then add it to row I to get a new row I. Okay, and so those are the row operations. This should be very similar to when you solve a system of equations using elimination. And we're just not using the variables essentially. Okay, so here we have three matrices. So this example, perform the following row operations. We have matrix A, matrix B, and matrix C. We're actually performing the operation R1 swaps with R2. Okay, so to matrix A, so we have the matrix 2, 4, negative 3, 1, negative 8, 0. That's our augmented matrix. R1 swapped with row 2 transforms the matrix to 1, negative 8, 0, 2, 4, negative 3. Nothing too exciting. All we're doing is swapping the rows there. B here, we're actually performing the operation negative 1, 6 times R3 to get a new row 3. And we want to do this to matrix C. All right, so the way what we do here is take our old matrix here, 2, 1, negative 8, 4, 0, 1, 4, negative 2, and 0, 0, negative 6, 24, and that's the dotted line goes right there. Okay, so we're primarily working with this row here, at least, right? So we're going to multiply each element or each entry there by negative 1, 6. All right, so doing that to get a new row 3, we would get the two first rows, 2, 1, negative 8, and 4, stay exactly the same. Row 2 stays exactly the same. But the second row here, we're multiplying everything by negative 1, 6. So we take 0, which is the first entry in row 1, multiplied by negative 1, 6, you get 0. The second entry in row 3 is a 0, multiplied by 1, negative 1, 6 is 0 as well. But then we have a negative 6 times a negative 1, 6, so that would give us a product of 1. And then the last entry in row 3 is a 24. So 24 times a negative 1, 6 would give us a negative 4. And that would be the new matrix. All right, the next matrix here, we have basically taking our matrix B here, 1, negative 1, and 2, 4, negative 8, 0. And we're performing the operation. We're going to multiply row 1 and then add it to row 2 to get a new row 2. And that means the first row will stay the same, but the second row will change. On the side here, I like to write it like this. Here is row 2. So row 2 is 4, negative 8, 0. And then I'm going to multiply that row by negative 4. Okay, and then I'm going to multiply row 1 by negative 4. So I would get negative 4, positive 4, and negative 8. And then I'm going to add these to get a new row 2. So we would get 0, negative 4, negative 8. So my new row 2 would be 0, negative 4, and negative 8. And we could use these operations to rewrite an augmented matrix into row echelon form. All right, so we can solve a system of equations using Gaussian elimination. You could do the following. The first step is you write an augmented matrix for the system. Use row operators. Step 2, we use row operations to transform the augmented matrix into a matrix in row echelon form with ones down its main diagonals and zeros directly below the ones. Okay, step 3, when step 2 is complete, write the resulting equivalent system to find the solution, and then 4, check answers if necessary. Alright, let's try an example of that. Alright, so here we're actually solve the system by Gaussian elimination. So let's write the first step is to write the augmented matrix. So we have the augmented matrix 2, 1, 5, 1, negative 1, 4. That's the augmented matrix. Alright, so I'm going to interchange row 1 and row 2. So row 1 gets swapped with row 2 because I want to get ones down this main diagonal here. Okay, and this becomes a 1 if I swap the 2 here. So we're going to get the matrix 1, negative 1, 4, and then the second row is just 2, 1, 5. Alright, that's the new matrix. Alright, now I'm going to take that matrix and I'm going to use row 2. I'm going to type of row operation, and I'm going to multiply the first row by negative 2 to get a new row 2. Alright, so on the side here, I have row 2. Row 2 is 2, 1, and 5. And then I'm going to multiply in row 1 by negative 2, and then add the result to get a new row 2. So negative 2 times row 1 would be a negative 2, positive 2, and a negative 8. So adding these results gives us 0, 3, and a negative 3. So our new row 2 is those values there. Okay, the first row didn't do anything, so we just write the first row still. But my second row 2, or my new row 2 is 0, 3, negative 3. Okay. Alright, so we're almost there now. I got a 1 down the first diagonal, or first row. Now I need this to become a 1. And to do that, I will go ahead and multiply the second row by 1, 3 using a type 2 operation. So we'll multiply the second row by 1/3 to get a new row 2. Alright, so the first row stays exactly the same. Second row becomes now 0 times 1/3 is 0, 3 times 1/3 is 1, and then negative 3 times 1/3 is negative 1. Alright, and you wonder, why did I choose 1/3? Well, the idea is to make this a 1. And so basically, I just need to multiply by the reciprocal of that. And so that's why it's 1/3. Okay, so that's row echelon form right there. And now we use something called back substitution, but let's rewrite the new system. The new system is x minus y equals 4, and then 0x, right? 0x plus y equals negative 1. In fact, we don't really have to write the 0x, but that's what it would be. But notice we have y equal to negative 1. So then I like to call this back substitution, because now we're going to go plug that negative 1 back into the equation above it there to get x minus negative 1 equals 4. So that's x plus 1 equals 4. So that tells us x equals 3. Alright, and so the solution is the ordered pair 3, negative 1. Alright, let's look at another example of a bigger system. So solve the system by Gaussian elimination. First step is to write the augmented matrix. So we have 3, 1, 5, and 8. Next row is 2, 3, negative 1, and 6. Next row would be 1, 2, 2, 10. And that's our augmented matrix there. And we could do another swap here. Notice the main diagonal this time it would be this here. And we need to make all the diagonals of 1s there and 0s below it. And so we know we have a 1 there, so we can put that up there to swap it. And so we're going to swap row 1 with row 3 to get the new augmented matrix. 1, 2, 2, 10. Second row stays the same. 2, 3, negative 1, and 6. Then we got 3, 1, 5, and 8 since we swapped. Okay, so that's our new augmented matrix. All right, now, once again, I already have a 1 here. Now I want to get zeros below here. So I'm going to first make this 2 a 0 by taking advantage of this 1. So I'm going to multiply this first row here by negative 2 and then add it to equation 2. So that's a type 3 operation. So we're going to take row 2 and add negative 2 times row 1 to get a new row 2. All right, so the first row will stay the same. Second row is going to change. I'm going to do the scratch work on the side here. So row 2, I know is 2, 3, negative 1, and 6. Okay, and then I'm going to multiply row 1 by negative 2. And then add the results there. So then we would get a negative 2, negative 4, negative 4, negative 20. And this is going to give me a new row 2. So negative 2 plus a negative 2 is 0. 3 plus a negative 4 is negative 1. Negative 1 plus a negative 4 is negative 5. And then 6 plus a negative 20 is negative 14. So my new row 2 is 0, negative 1, negative 5, and negative 14. All right, and third row stays the same. 3, 1, 5, and 8. Okay, so now I'm going to use that 1 again in the first row to make the 3 a 0 here. So I'm going to multiply this first row by a negative 3 this time and add it to row 3. So I'm going to perform another type 3 operation by taking row 3 and adding a negative 3 row 1 to get a row 3. All right, so to do that, the first row stays the same. 1, 2, 2, 10. Second row stays the same. 0, negative 1, negative 5, and negative 14. But the third row will change. All right, let's do the work on the side here. So row 3 is 3, 1, 5, 8. I'm going to multiply by negative 3, row 1. And then add that to get to new row 1. Sorry, new row 3. So negative 3 times row 1 would be a negative 3, negative 6. Back up there a little. So negative 3, negative 6, negative 6, and then a negative 30. Okay, so now adding each entry, that gives us 0, negative 5, negative 1, and a negative 22. So our new row 3 is 0, negative 5, negative 1, and a negative 22. All right. So now I'm gonna so now notice we got a 1, 0, 0, which is exactly what I want. I need to make this a 1, so I'm gonna multiply through by negative 1. So let's take negative 1 and multiply by row 2 to get a new row 2. All right, so doing so, the first row stays exactly the same. Second row becomes 0 times negative 1, which is 0. Negative 1 times 1 is 1, which is what we wanted. Negative 1 times a negative 5 is a positive 5, and then negative 1 times a 14 is a positive 14. And then the third row stays the same. So we have negative 5, negative 1, and negative 22. And then that's going on the other side of the equal sign. Okay, so now we got the 1 like we wanted there. Now let's make this -5 here a 0. And to do that, we could use let's see, the 1 here. So then we'll take this second row here, multiply by a +5, and add it to row 3. Okay, so we'll row 3 and add a 5 times row 2 to get a new row 2. New row 3. Alright, so first row stays the same. We have 1, 2, 2, 10. Second row 0, 1, 5, and 14 still stays the same, but the next row here will change. So we have row 3, which is 0, -5, -1, -22. Then we're going to multiply row 2 by 5. And so we get 0 times 5, which is 0. 1 times 5 is 5. And then 5 times 5 is 25. And then 5 times 14 is 70. Okay, and then we add this to get a new row 3. So 0 and 0, 0. 5, -5 and 5 is 0. That's good. -1 and 25 is 24. -22 and 70, adding those up gives us 48. So our third row becomes 0, 0, 24, 48. Okay. And now we got a 0 below, so we're almost there. We just need to make this a 24-1, and that's going to be pretty easy to do by dividing by 24 or multiplying by the reciprocal. So I'm going to multiply row 3 by the reciprocal 24. So let's multiply row 3 by 1/24 to get a new row 3. Alright, so doing so will give me, well, the first row stays the same, 1, 2, 2, 10. Second row stays the same, 0, 1, 5, and 14. And then, of course, the next row would be 0, 0, 1, because we multiply by 1/24, right? The zeros in 124 times 0, 124 times 0 is still 0, 0. But then 24 times 1/24 is 1, and then 48 times 48 is 2. Okay, so we got our row echelon form matrix because we have ones down the diagonal and zeros below the diagonal. Okay, so now that we have it in row echelon form, let's rewrite the new system. So we have x plus 2y plus 2z equals 10. Then we have 0x plus y plus 5z equals 14. And then we have z equals 2. All right, substituting back, we see we have y plus 5 times 2, which is 14. So y plus 10 equals 14, which tells us y equals 4. Okay, so now plugging both z equal to 2 and y equal to 4 back into the first equation, we have x plus 2 times 4 plus 2 times 2 equals 10. So we have x plus 8 plus 4 equals 10. So we have x plus 12 equals 10, which tells us x equals -2. And we can see that the solution is -2, 4, and 2. Okay, next question here. Solve the system by Gaussian elimination. So our augmented matrix here is 1, 1, -1, -3, -3, and -5. Okay, so it's almost already in Gaussian elimination. We just need to make this a -3 here is 0. And to do that, we could take, say, row 2 and add +3 times row 1 to get a new row 2. I should just decide just a tad there. Alright, so what is row 2? Row 2 is -3, -3, -5. And then we need to multiply row 1 by 3. So that would give us 3, 3, -3. And then add the results to get a new row 2. So we get 0, 0, negative 8. Which gives us the augmented matrix 1, 1, negative 1, 0, 0, negative 8. And then notice that we are not going to be able to get a 1 no more in this particular entry. And the reason is if you rewrite the new system here, we have x plus y equals negative 1. And the second equation means we have 0x plus 0y equals negative 8, which simplifies to just 0 equals negative 8. That's no good. That's a contradiction, right? That's no solution in this case. Means the lines don't intersect. It's inconsistent, right? The system's inconsistent, and the equations would be independent. All right, what about the next equation system? So the augmented matrix here would be 2, negative 1, 4, and then negative 6, 3, and negative 12. Okay, so to do this, I'm going to make this first entry here a 1. So I'm going to go ahead and multiply through by 1/2, row 1, to get a new row 1. All right, doing so would give me 1, right? 2 times 1/2 is 1. Negative times 1/2 is a negative 1/2. 4 times 1/2 is 2. All right, second row stays exactly the same. Now I need to make that negative 6 a 0 by using the first row. So we're going to take row 2 and add a positive 6 times row 1 to get a new row 2. Okay, so what's row 2 look like? Row 2 is negative 6, 3, negative 12, and then we need to multiply row 1 by 6. So we would get 6 times 1, which is 6, 6 times negative 1/2, which is negative 3, and then 6 times 2, which is 12. And that will give us a new row 2. We get 0, 0, and 0. So this is very similar to the last one. First row stays the same, but the new row is 0, 0, 0. So if we rewrote the system here, this would be x minus 1/2 y equals 2, and we would get 0x plus 0y equal to 0. The difference is this here is 0 and this is 0. That's an identity, that's a true statement. This would indicate we have infinite solutions. Dependent equations for sure. And I guess this system would be consistent. All right, Gaussian elimination works well with higher order matrices. It basically hides the x's and y's. All right, so that's it for this video.